All right, let's go now for our very important theorems that are the heart of this chapter. So as we said earlier, there's going to be actually three uh, important theorems. The beppo-levi, Lebesgue-dominated convergence, parameter-dependent integral, and theorems for parameter-dependent integrals. Actually, all of these can be more or less summed up by Lebesgue-dominated convergence theorem, but let's go step by step and look at the first one for today, the monotone convergence theorem. And it has actually three ways of describing it. The first one for increasing sequence, and as corollary, so this theorem, we can apply this one to series and also expand it to decreasing sequences. Okay. Let's go. So beppo-levi, here is beppo-levi. Beginning of the variant of the 18th century, beginning of the 19th century, beginning of the 20th century. The beppo-levi monotone convergence theorem for Lebesgue integral. Okay, so let's at least remember the title, monotone convergence, meaning that we need to have monotone convergence of sequence of functions, and we want to decide for the integral of these ones. So let's read that very carefully. So we've got an increasing sequence of function, but what does it mean increasing? Because it's functions that depend on x, functions of x, but that also depend on n. But it's increasing as a sequence, meaning it's pointwise increasing. So let's maybe put that into several small pieces. Pointwise increasing. What does it mean? So we've got this sequence fn of x. And I want it to be increasing as a sequence. What does it mean? It means that for fixed value of x, for x in the domain of f, in R, because if we want to restrict it again, we can use an indicator function. For any x in R, I want that f of n plus 1 of x is, if I want it to be increasing, I want it to be greater or equal to fn of x. Okay. It doesn't mean that the function fn of x as a function of x is increasing. It means that the sequence of values, if I look pointwise at my function, that's going to be increasing. Example, let's take directly an interesting example. That's one function of x, right? Let's say that it's fk for some k of x, right? This function as a function of x is obviously decreasing. Great, right? But now if I'm drawing, let's say this one, let's say that this is fk plus 1 of x. As a function of x, it's still decreasing, but as a sequence between indexed by k, for a fixed x value, the value fk of x and the value fk plus 1 of x are ordered like this. Fk plus 1 of x is greater than fk of x. So as such, this is an pointwise increasing sequence. Okay, so for fixed x, the value at rank n is smaller than the value at rank n plus 1, right? So this is what we have for all x. We want it to be positive first. We want it, so 0 is the smallest one, smaller than fk of x, smaller than fk plus 1 of x, smaller than what? Whatever. Okay, it can go up to infinity. All right, so let's assume that we've got that this is pointwise converging almost everywhere to some function f. Okay, don't worry about the fact that it's sub. It doesn't really matter. It's just that you've got almost everywhere pointwise convergence to a function. Then we have what we said we wanted to be able to decide for, that the limit of the integral is equal to the integral of the limit. And what is the integral of the limit? Well, it's the integral of the limit function, f of x. Okay, right? So let's apply this. Let's see this one. Okay, so I want to determine the limit as n tends to infinity of this function. So the first thing is, let's make clear what is the sequence of functions we are looking at. This, I hope, is pretty clear. That's going to be cosine of x over n times the indicator function of 0, 1 of x. Okay, what is that in other terms? That's the function that is equal to 0 if x doesn't belong to 0, 1, and it's equal to cosine of x over n if x is between 0 and 1. Okay, so well, let's draw some of that. Let's draw some of that, I said. All right, so let's cosine of, so for n is equal to 0, it doesn't exist. Cosine for n is equal to 1. For n is equal to 1, my function is going to be, well, of course, equal to 0 everywhere outside of 0, 1. That's the first thing. Let's say that 1 is here. And cosine x, 1 is smaller than pi over 2, so it's going to be something like this. Okay, so that's my n is equal to 1 function. N is equal to 2, what do we get? So you can try to draw it. For n is equal to 2 again, it's still going to be equal to 0 between minus infinity and 0 and after 1. And cosine x over 2, so that's going to be something, well, it's going to be again 1 at 0, and cosine n over 2, that's going to be something a bit bigger, right? And we can go on, cosine n over 3, for n is equal to 3, n is equal to 3, so again, it's going to, well, maybe we should change color. For n is equal to 3, again 0 here, and then for n is equal to 3, that's going to be something, something a bit bigger, okay? X over 3, right? So the period is multiplied by 3, right? So what do we get? So let's find the limit. The pointwise limit, okay? So pointwise limit. Okay, for x of x over n. Let's split that into several parts. For x over n as n tends to infinity, right? So that tends, of course, obviously, for x between 0 and 1, that tends to 0. So cosine of x over n as n tends to infinity, that's going to tend to cosine of 0, which is 1. Okay, so at the limit, we've got this, right? So the limit function, the pointwise limit almost everywhere, but actually really everywhere, fn of x as n tends to infinity. So sorry for my n being very similar to my x. I'm trying to correct that year after year. That's going to be the function that is 1 between 0 and 1 and 0 everywhere else. So that's exactly going to go to the indicator of 0, 1 of x, right? Now, is it pointwise increasing? Do we have that fn plus 1 of x minus fn of x greater than 0? So let's see. That's cosine x over n plus 1 minus cosine x over n. Okay, so let's see. X over n plus 1, x over n plus 1 is smaller than x over n, at least for x small enough, but at least for x, for all x between 0 and 1, we've got that. Well, that is true in any case for all x positive, but we also have that for x between 0 and 1, the cosine function is decreasing. So this is going to be between 0 and between 1. So this is a decreasing function, so that cosine of x over n plus 1 is going to be bigger than cosine of x over n. Okay, the closer we are to 0, the bigger the cosine is, right? So pointwise, this is an increasing function, right? And so we are really satisfying. So fn of x is pointwise increasing. It is also positive because the cosine is always positive in that on that domain. It's positive. It's pointwise increasing. We've got that fn of x tends to, as n tends to infinity, to the indicator function. Well, fn, the sequence fn, tends as n tends to infinity to the indicator function of 0, 1. So this is it. I've satisfied the hypothesis of beppo-Levi. So pointwise increasing converges pointwise to some function. We can apply the conclusion of that theorem, which tells you that the limit of the integral of cosine n over x 1, 0, 1 of x dx, the limit as n tends to infinity, is equal to the integral of that limit x over n, sorry, x over n, sorry, that's not very nice, x over n, x over n, times the indicator function. That pointwise limit, we saw that that would be the integral of my indicator function. And this, of course, is equal to 1, right? That's the function that is 1 between 0 and 1. So that's that integral is clearly defined as 1, right? So we have that this limit, using the beppo-Levi theorem, is equal to 1, okay? Right? That's it for the main theorem, the beppo-Levi theorem, and then we will have the two next corollary to this theorem. So the next two corollaries to this theorem, so I propose that you work them alone. What are they? They are very simply said that we can consider series as specific kinds of sequences, because if you consider the series of the partial sums, well, the partial sums, that makes a sequence, right? So we've got exactly the same idea. So we can apply it to series, to positive with positive terms, exactly the same way. So if we've got convergence on both sides, if we've got convergence of the series towards some specific function, so remember what we did in year 2 about power series, for instance, then we have that it's equal to the sum of the integral of the series of the integral. Okay, but that's something we've already used actually when we were dealing with power series last year. Okay, so that's one application. Sorry about this. One example of application. Right, so try to do this one. And next, we've got the same kind of thing for decreasing sequence, as long as we've got monotonicity, with one more hypothesis, which is, so in the case where we've got decreasing sequence, it has to be positive, we need the first one to be integrable, okay? We need f1 is integrable. Then if f1 is integrable, then the integral of the limit is equal to the limit of the integral, and it is integrable. Okay, and this is a technical need, so that um, we can actually apply the positive the monotone convergence theorem for increasing sequence when we apply it to f1 minus fn. That's defining a new sequence, which this one is going to be increasing. If fn is pointwise decreasing, then gn here defined is increasing. But in order to be able to apply this theorem, we will need to have integrability of f1, and then it works the same way. So you can try to apply it on that example to see how it works in that case. That's it for today. Thank you very much.